Okay, picture this. Imagine an engine so incredibly powerful that it can take a practically motionless particle and just violently whip it up to the absolute speed limit of the universe in a fraction of a second. Normally, you'd think, right, we have to look to the deepest, darkest corners of some distant galaxy to find that kind of terrifying horsepower. We usually associate that level of extreme physics with, I don't know, supermassive black holes or dying stars. But as we're going to see in this explainer, one of the most violent astrophysical engines ever discovered is humming away right now, literally right in our own cosmic backyard. We're talking about Jupiter's bow shock accelerating electrons to light speed, and it is absolutely mind-blowing. So let's dive into this massive universal mystery. For decades, scientists have been plagued by a persistent and honestly kind of unnerving puzzle. Where exactly do cosmic rays come from? I mean, think about it. Earth is constantly, and I mean constantly, being bombarded by these high-energy particles zipping through space at terrifying speeds. They tear through the cosmos, strike our atmosphere, and even penetrate deep underground. We know they're out there, and we know they're hitting us. But pinning down their local origins? That's been incredibly difficult. We just lack the ability to see exactly how a particle floating in space suddenly gets accelerated to such extreme destructive velocities. But the answer, it turns out, was waiting for us at the fifth planet from the sun. Now, to really get how this mechanism works, we need to completely shift how we view our local gas giant. Jupiter is far more than just a beautiful, swirling ball of clouds. Its environment is, without a doubt, one of the most vicious in the entire solar system. It's a hostile, radiation-filled monster. Like, if you were to just drop a standard unshielded spacecraft into the wrong part of this neighborhood, its electronics would be fried in an absolute instant by a relentless gauntlet of extreme physics. It's an incredibly violent region of space that fundamentally alters everything that dares to pass near it.
The reason for all this overwhelming viciousness really comes down to Jupiter's magnetosphere. Jupiter possesses an incredibly strong magnetic field, but it doesn't just act as some gentle, invisible force field protecting the planet. Instead, it acts as a chaotic swirling inferno of charged particles. This magnetosphere is so gargantuan, so mind-bogglingly immense, that if it actually glowed in the night sky, it would look significantly larger than our full moon from Earth. Let that sink in. It is an astronomical behemoth, creating the absolute perfect arena for some of the most violent physics in the solar system to play out.
And what's really interesting here is the shocking contrast that sets the stage for our engine. On one side, you have the relatively quiet, empty vacuum of deep space. But on the other side, you have the solar wind. The solar wind is essentially this relentless, violent stream of charged particles constantly being blasted out by our sun. When this supersonic wave of solar material travels across the solar system and just smashes directly into Jupiter's massive magnetic shield, well, all hell breaks loose. It's at this exact chaotic plasma boundary where the irresistible force meets the immovable object that the engine actually sparks to life. But, of course, to actually see this engine at work, we couldn't just use telescopes from Earth. We needed to get dangerously close to the source. Enter NASA's Juno spacecraft. Arriving at Jupiter in 2016, Juno acted as our brave robotic investigator. Because Jupiter's radiation is, as we said, totally lethal to standard circuitry, Juno had to be heavily armored in thick titanium just to survive the fatal radiation bursts. I mean, it was designed to deliberately plunge directly into this high-stakes danger zone, carefully mapping out the planet's intense gravitational and magnetic secrets just to figure out exactly what was happening at this incredibly turbulent boundary. So what did Juno find? Well, it gave us a front-row seat to a fascinating phenomenon known as a bow shock. Think about a massive, heavy cargo ship plowing at full speed through the ocean, right? As the bow of the ship cuts forward, the water violently piles up, compresses, and breaks in a massive turbulent wave right at the front. The exact same thing happens in space, just on a cosmic scale. The solar wind is the ocean, and Jupiter's magnetic shield is the ship. As the solar wind crashes in, it violently compresses against the magnetic field, creating an enormous, invisible shockwave in the plasma that stretches for millions of miles. Here is where the mechanics of the engine actually kick into high gear. As the solar wind crashes in and that massive bow shock forms, the boundary doesn't just sit there perfectly smooth. The collision gets incredibly messy, creating what physicists call a transient foreshock. Sounds complicated, but it's basically a highly unstable, deeply turbulent region bubbling just ahead of the main shockwave. Think of it like a swirling cosmic trap. Electrons sweeping in from the solar wind get caught in this severe magnetic instability. They get ping-ponged, bouncing back and forth, violently gaining kinetic energy with every single bounce. And then, the magnetic field suddenly snaps. It acts as a ruthless cosmic slingshot,
firing those trapped, highly energized particles completely out of the system.
Now, you might be wondering, why does this magnetic slingshot happen at Jupiter and not just anywhere? Like, we have bow shocks here at Earth, too. Well, the answer is incredibly simple. Scale. Scale explains everything. Jupiter's bow shock is on an entirely different level. The sheer, incomprehensible magnitude of Jupiter's magnetic boundaries provides a massive runway. Just like an airplane needs a super long stretch of tarmac to build up enough speed for takeoff, this massive glowing curve in space provides the enormous runway needed for the magnetic slingshot to really wind up. Without that immense space, particles simply wouldn't have the time or the distance to bounce back and forth enough to reach such extreme energies.
And that brings us to the massive payoff of Juno's data. When that Jovian slingshot finally fires, it doesn't just give these electrons a gentle nudge or a slight boost in momentum. No way. The massive bow shock accelerates these simple electrons to relativistic velocities. We are talking about speeds approaching 300,000 kilometers per second. It accelerates them literally right up to the speed of light. This isn't theoretical math on a chalkboard. This is a localized, naturally occurring engine taking a particle from a relative standstill and pushing it to the absolute maximum speed limit of the universe in a matter of moments.
The absolute thrill for scientists surrounding this discovery was that Juno didn't just infer this was happening from millions of miles away. Juno's sensors caught these relativistic electrons absolutely red-handed. By flying directly through the precise region of the bow shock, the spacecraft's highly sensitive instruments detected an intense, undeniable spike of near-light-speed electrons right in the act of being accelerated. It was a phenomenal breakthrough. It provided the direct, smoking gun observational evidence that the scientific community had been desperately waiting for to prove this extreme acceleration mechanism is highly active. Which brilliantly illustrates our ultimate takeaway for this explainer. By seeing this incredible beam of energy shooting out into the void, we realize Jupiter is essentially acting as an incredible, accessible, local physics lab for us. Because its colossal bow shock mirrors the exact same physics that happen in massive supernova remnants and incredibly distant hyperactive galaxies, we can study those phenomena right here without leaving our solar system. By understanding the inner workings of this near-right speed engine, we finally unlocked a massive piece of the puzzle regarding how massive astrophysical events across the entire universe generate the dangerous cosmic rays that constantly bombard our planet. Which leaves us with this final, honestly thrilling thought. If a single gas giant in our own relatively quiet solar system is capable of generating the sheer magnetic violence required to slingshot particles to the speed of light, what other unimaginably massive magnetic engines are lurking out there in the deepest, darkest corners of the cosmos? If this is what our local neighborhood is capable of, the rest of the universe is surely hiding particle accelerators that dwarf our wildest imaginations.